Okay, so we are going to be learning how to name alkalines today, um, or alkanes actually. And we're going to do a little review first on some of the things we learned in the earlier weeks. So, how do we determine how many valence electrons a particular element has? And so in this case, we're looking at potassium. And if we look at the periodic table, we see that it has 19 electrons. So in the first valence, we're going to have 2. Now, each valence after that has 8. So we're just going to start adding them up until we reach that 19. So we start off with the first, which always has 2. And then the next valence, we have 8. That's 10. The next one, we have 18, which means on the outside valence, we're going to have 1. So we're just adding up to that number that an element has in the periodic table. Now that's one way to figure it out. Another way to figure it out is to look directly at our periodic table. And in our periodic table, going up and down are groups. So we have group 1, group 2. We're going to skip this middle section because that middle section just gets weird and doesn't apply. Group 3, group 4, group 5, group 6, group 7, group 8. And depending on where in a group something is, that's how many electrons it has on its outer shell. The only exception is helium, because it has 2, it's completely full. It doesn't even can't even get up to 8. So if we were to look at, say, aluminum is in group 3. It has 3 electrons in its outer shell. If we were to look at, so we did potassium, calcium would have 2 in its outer shell, and actually everything in this group going up and down would have 2. Everything in this one right here would have 3. Carbon, 4. I'm not even going to try to pronounce that. Chlorine has 7 on its outer shell. Argon has 8. So either way, they both work out, whatever choose. So if you get a question about how many valence electrons are on the outermost shell, that's the easiest way to go about it. The 2 ways to go about it. So we're actually are talking about alkanes today. And so, but specifically how to name them. So if we saw a molecular structure and we recognize it's an alkane, how do we go about creating a name? And the first step is to find the parent hydrocarbon, right? And then number the atoms in the chain. So we would count how many carbons go along in the chain. We identify and number the substituents, and then write the name as a single word. Now that seems very linear and easy. Trust me, it'll get more complicated. And to the point where I'm going to let someone else explain how to do this. Today we're going to look at a lot of videos because quite frankly, there are other people who do a lot better job at this. So let's take a look, see what Josh has to say about naming alkanes.
In this question, we want to figure out what the relationship is between these two compounds. And because they're drawn so differently with bonds kind of going in different directions, it's pretty hard to even tell if they're identical compounds, if they're isomers, what they are. So let's go ahead and first just generate a basic name, ignoring the stereochemistry for each of these compounds. So first we'll find, as always, our longest continuous carbon chain. In this case, we have this 8 carbon chain. All right, and in this other compound. Hopefully you can see that, again, this is our longest chain. Okay, then if we number these, starting on the end closest to the first substituent, get that one numbered like that, and this one numbered from left to right. Okay, so for both of these, we have an octane chain with methyl groups at carbons 3 and 4. So both have the general name 3,4 dimethyl octane. So we know they must be some sort of isomers or identical compounds. And we could start doing bond rotations or manipulations and try to make them look alike to see if they're identical or enantiomers or what they might be. But sometimes when we have a compound like this, it's easiest just to assign RS configurations to our chiral centers and then work from there. Okay, so we have chiral centers at carbons 3 and 4. Okay, so let's look at the stereochemistry around carbon 3 first. And if it helps, you can go ahead and draw in this hydrogen. It's pointing out. So hydrogen is our priority 4 group. Then we have a carbon connected to a CH3, a carbon connected to 2 other carbons, and just a CH3. So this carbon connected to 2 other carbons is going to be our priority 1 group. This carbon is our priority 2 group, and this methyl group is our priority 3 group. Okay, so now, as we normally did this, we would just flip this over so we get the priority 4 group pointing to the back. But there is a trick we can use. We can leave this priority 4 group pointing out and then just reverse the configuration that we think we have. So we go from 1 to 2, 2 to 3. We're going around to the right. It looks like R, but since priority 4 group is pointing out, it's actually S. Okay, so at carbon 3, we have S configuration. Okay, now let's do our stereochemistry around carbon 4. Okay, if it helps, we can draw in our hydrogen as a wedge pointing out. Okay, and assigning our configurations. Here's our priority 1 group. This would be our priority 2 group. The methyl is our priority 3 group, and the hydrogen's priority 4. We'll draw an arrow from 1 to 2, 2 to 3. Okay, so we're going around and it looks like R, but since H is pointing out, it's actually S. So at carbon 4, we have S configuration. So we have 3s, 4s. Okay, so this compound has the name 3s, 4s. Three, 4 dimethyl octane. Okay, so we can do similar assignments around both of these stereocenters in this compound. In this case, carbon 3, we have the hydrogen pointing back. Prioritize our groups. Priority 1, 2, 3, and 4. In this case, our hydrogen's pointing back, so we just take the configuration as we see it. Draw arrows 1 to 2, 2 to 3. This is going around to the right. So on carbon 3, that's our configuration. Okay, at this other stereocenter, since we have 2 bonds in the plane, 1 bond pointing back, our hydrogen's pointing out. And that's our priority 4 group. This would be our priority 1 group. This is our priority 2 group. Priority 3. Going from 1 to 2, 2 to 3. It looks like S, but since priority 4 is pointing out, it's actually R. So we have 4R. So this, the name of this compound, is 3R, 4R. 3, 4 dimethyl octane. Okay, so in this case, we have a perfect switch in configurations. At carbon 3, we go from S to R. At carbon number 4, we go from S to R. Since all of our stereocenters switch configurations, we can classify this pair of compounds as a pair of enantiomers. So rather than trying to manipulate the bonds or redraw the compounds, sometimes it's just easier to assign your configurations and see how they switch.
All right. And much like what Josh showed you, I like using this guy a lot. So we'll let Wayne tell you about the structure of methyl hexane.
Let's write the structure for 3-ethyl-2-methyl hexane. We'll also look at the molecular formula, and that is C9H20. So to start out with, we have hexane. When we see ANE on the end of the compound here, ANE, that tells us we have an alkane, and the carbons, they'll be single bonded to each other. Hex tells us that we'll have 6 carbon atoms. So we're going to have 6 carbon atoms single bonded. That'll be the longest chain here in our structure. So here's our hexane, and these lines here, they represent a bond to a hydrogen atom. So let's number the chain, starting with 1. So we'll have 6 carbons, that's our hexane, and on the second carbon, we're going to have a methyl group. So a methyl group, that's just a carbon with 3 hydrogens. Let's put that in. Right next door to that, on the third carbon, we have our ethyl group. An ethyl group, that's two carbons bonded together with single bonds. I can either put it up here or down here. Let's move it down here to give ourselves some room. So this is our structural formula for 3-ethyl 2-methyl hexane. We have our long chain here, hexane, and then on the second carbon we have the methyl group. On the third carbon we have the ethyl group. We list ethyl first because it comes before methyl in the alphabet. Sometimes you'll see this written out like this here. And again, you have 1, 2, so on the second carbon you have your methyl group, and on the third carbon here you have the ethyl group. It's right here. It doesn't really matter if we put this on the bottom or the top because these single bonds, they rotate. This is Dr. B with the structural formula for 3-ethyl 2-methyl hexane, and the molecular formula for 3-ethyl 2-methyl hexane is C9H20. Thanks for watching.
He makes it seem so easy. So a conformation is what he was talking about, where you can just rotate an atom and where we look at it from a different angle. So that's just it's the same structure, it's just rotating. So just keep in mind that these atoms, when we make the models, like, they're obviously static, but in reality atoms have a lot of movement going on with them, with the protons, electrons, and neutrons. So this is just another model. It's called the sawhorse representation, and that's because it's kind of set up 3D and to be linear at the same time, just like a sawhorse. Another way we can represent what's going on with an atom is what's called a Newman projection. And two things to point out is, in a staggered situation, bonds are far away and viewed end on end, where in eclipse they're close. So over here we can see a staggered, and it's pretty easy to see everything. It's like we're just looking straight down at them. Where in eclipse they're so close they almost go over each other. And oftentimes if we were looking at them, they would cover each other, and that's why we call them an eclipse. So what we're going to look at is a good set of videos. I think like 5 or 6 of them. Some of them are going to kind of go over, one of them is going to go over this Newman projection and how to draw it. The others are going to go over review and how to do ground state configurations. So we started off talking about those at the beginning of the class, and I just want this to be a review for you, and it's going to go over how to do particular ones. So for the rest of this video, it's going to be actually watching other people's videos. And so let's start off with Newman projections, brought to you by David Lever.
So you should be able to see my screen, and I'm going to work on the Newman projections for 1-chloropropane. I'm actually going to approach this a slightly different way than you may have. The first thing I always recommend doing, of course, is writing the molecule to make sure you actually have the right structure. So 1-chloropropane will have a Cl, and then a CH2, and a CH2, and another CH3. And if we number those carbons, carbon 1 is the one that has the chlorine attached. So what we want to do is look down the carbon 1 to carbon 2 bond. The next thing I would do is I would take that and draw that in a full kind of dashed wedge structure. So you're actually showing what's attached to the 2 carbons that you're going to be looking down. We don't need to show the dashed wedge on the carbon 3 because we're not actually looking down that bond. Oops, these are hydrogens, not chlorines, sorry. Right, so we've got a Cl on the first carbon and a CH3 on the second carbon, and all the other substituents are hydrogen. So then what we want to do is we want to look down the bond from C1 to C2. So this will be my front carbon, and this will be my back carbon, and I'll be looking down that bond. I've automatically drawn this in the most stable conformation that puts the chlorine and the CH3 in the anti-position. And it's usually productive to try to draw the most stable conformer first. So on my back carbon, the way I've written it, I've got a CH3 pointing down, and I've got hydrogens out here, and then on my front carbon I've got a chlorine pointing up and the 2 hydrogens out like this. So that's the anti-conformation. That's going to be the most stable. The least stable conformer is going to be the one that eclipses the chlorine and the CH3. So I can go up here and I can draw my least stable conformer. And it doesn't really matter which one you leave. I'm going to leave the front carbon with the same conformation with the chlorine up, and then I'm going to rotate the back carbon to put the CH3 group up here. And I'm making sure that I only have one of these substituents on the back carbon between each set of the 2 on the front carbon. So just this hydrogen is here. This one doesn't want to be down there. It wants to be in between the chlorine and the hydrogen. So that's the least stable. And what we've got is an eclipsing steric strain here between the 2 big groups. And then we've got 2 eclipsing torsional strains. And we actually know that each of those is about 1 kilocalorie per mole. So we've got 2 kilocalories per mole eclipsing torsional strain there, and then we've got some eclipsing steric strain. We know that's going to be much more than 1 kilocalorie per mole, but we don't know exactly what it will be. So then we'll go for the gauche conformers. Right. There's basically no strain here because the chlorine and the methyl group are not interacting, but they're going to be 2 gauche conformers. Right? And again, I'm going to leave the front carbon alone, and I'm going to rotate the back carbon to put the methyl group either here on the right, or alternatively the mirror image that puts the methyl group here on the left. And those are going to be equivalent in energy, and what we're looking at here is a gauche torsional strain. We don't know what the magnitude of that gauche torsional strain is between a chlorine and a CH3 group, but we can infer that it's probably less than the gauche torsional strain between 2 methyl groups. Because chlorine, although it's much more massive than the methyl group, because the nucleus is larger, it's probably not a larger volume than the CH3 group, because the CH3 group actually has 4 nuclei. So in terms of the amount of steric strain, chlorine is going to be smaller sterically than CH3. It's also polarizable, which means the electron cloud can shift a little to try to get away from the other, to try to minimize the repulsion, especially in the eclipsing. And the carbon-chlorine bond is quite a bit longer, which means that the chlorine is probably not right over the methyl group, it's probably up a little bit. And then I'm looking for the other eclipsed ones, which will have the chlorine eclipsed with a hydrogen and the methyl eclipsed with a hydrogen. So again, we'll leave that front carbon alone, and we want a conformer that has the methyl group over this hydrogen, but then we're also going to have a mirror image conformer where the methyl group is over this hydrogen instead. So you'll notice that these 2 are mirror images of each other, and these 2 are mirror images. And in these we have a hydrogen over hydrogen, that's an eclipsing torsional strain, a hydrogen over methyl, that's another eclipsing torsional strain, and a hydrogen over chlorine. Those are all eclipsing torsional strains. We know this one costs about 1 kilocalorie per mole, and we know this one costs about 1.3 kilocalories per mole. We don't know what this one costs, but we're pretty sure that 2.3 plus whatever that is going to be more than this gauche torsional strain. Right? So we know these gauche conformers, because they're staggered, are lower in energy than the eclipsed. So this is our most stable. These 2 are equal in energy and a little bit less stable than the anti. And then we have to decide whether the eclipsing steric strain is going to be significant enough to make this one higher in energy than that one. And it will be. Right? We've got a minimum of 2 kilocalories per mole plus the eclipsing steric strain. Here we've got 1 plus 1.3 of 2.3 kilocalories per mole plus whatever eclipsing torsional strain we have here with HCl. We can be quite certain that the methyl over chlorine steric eclipsing strain is larger, that is more than 0.3 larger than the hydrogen over chlorine eclipsing steric strain, or torsional strain. This one's only a torsional strain, this one's a steric strain, and the steric strains are always larger. So then if we want to, we can actually start rotating. We can say, okay, this one would be my 0 degree conformer, and then if I start rotating it to the left, right, I rotate this methyl group over here, this would be number 2, that would be 60 degrees. I keep rotating it, number 3 would be this one here, which would be 120 degrees. Keep rotating it, 180 degrees would be where I have the eclipsing steric strain, and then I rotate a little bit more, and I'd have my 240 degree conformer, and then I rotate a little bit more, my 300 degree conformer, and then if I rotated this a little bit more, that CH3 group would come back down and be back to 0 degrees. So I could actually plot those on a graph. So that's the conformers that you want for the 1-chloropropane. You'll notice that the energy diagram for that is going to look identical if we put energy on the y-axis and the reaction coordinate. Right? And we start with the anti-conformer here at 0 degrees. And then we go up to 60 degrees, 120, 180 is going to be the highest energy, 240, 300, and then back to 360. It's going to look identical to the energy diagram for butane, where you've got a ghost strain here, you've got eclipsing torsional strains here, and then this high energy one, you've got the eclipsing steric. And it has that traditional, giving you the finger with your knuckles there, which you'll expect to see very similar to butane. Right, the overall shape is identical to butane. The only thing is that the energies will be slightly different. So that's the quiz. Are there any questions? I'm going to stop this recording.
Hey everyone. We are asked to provide the ground state electron configuration of boron in the standard and noble gas notation. So I recommend you take a minute now and try to solve this problem on your own before we go through the answer together. When finding the ground state electron configuration of an atom, we are being asked where does this atom place its electrons, i.e. what shells and orbitals are its electrons most likely to be found in. So to solve this, the first thing we need to do is look at our periodic table and see how many electrons our boron atom actually has in its ground or unexcited state. This is the same as its atomic number. Looking this up, we find out that boron is number 5 on the periodic table, meaning that in a neutral state, no positive or negative charge, our boron will have 5 protons and thus 5 electrons surrounding the nucleus. Let's also remember in the past videos we talked about this handy device for remembering which orbitals have the lowest energy, as these are the orbitals that are going to get filled first. Also, we learned previously we always begin filling the 1s orbital first, as it is the lowest possible energy state. Therefore, we will place our first 2 electrons in this orbital. Then we move to the next lowest energy state orbital, which is 2s. This orbital can also hold 2 electrons. Therefore, we place our 3rd and 4th electron here. Next, we can place our remaining electron in any of the 2 p orbitals, as they are all equivalent energy states. We can now write the ground state electron configuration of boron like so: 1s2, 2s2, 2p1. To write this electron configuration in noble gas notation, we just go to our periodic table and find the noble gas closest to boron with less electrons. This is going to be helium, which has a 1s2 electron configuration. Therefore, we can just substitute our 1s2 with helium like so. This is going to be much more useful when you're writing the electron configuration of larger elements. Thank you for checking out this video, and I hope it helped your understanding of boron's ground state electron configuration. If you enjoyed, please like, subscribe, and consider checking out our YouTube memberships by clicking that join button down below. However, if you have any comments, questions, or concerns about the information I provided in this video, please leave a comment down below and I will do my best to address your concerns.
To write the electron configuration for phosphorus, we need to find the number of electrons in the phosphorus atom. And we can do that by going to the periodic table, finding phosphorus, and looking at the atomic number. That's the number above the element symbol. It's a whole number. That tells us the number of protons, but it also tells us the number of electrons. And we can use that number, the number of electrons, to write the electron configuration for phosphorus. For phosphorus, we have 15 electrons. So we'll use the chart on the right to figure out the electron configuration. So we'll go down the first row, and we have 1s. So the first term is the 1s orbital. S orbitals can hold up to 2 electrons. So we'll put 2 in this first orbital here. We'll go down the next row, which is the 2s, and in the 2s orbital we'll put 2 electrons. In the third row, we go down, and the first term is 2p. P orbitals can hold up to 6 electrons. So in the 2p, we'll put 6 electrons, and we've used 10 electrons so far. In that third row, after the 2p, we have the 3s. We'll put 2 electrons in the 3s. We've used 12. We're in the fourth row, and the first term is 3p. We can put up to 6 electrons in a p orbital, but here, since we've already got 12 in the orbitals before it, we only need to put a 3. That'll give us 15. We have 2 plus 2 plus 6 plus 2 plus 3. That equals 15, the number of electrons in phosphorus. So this is the electron configuration for the phosphorus atom. And this is Dr. B. Thanks for watching.
Hello everyone and welcome to the One Class channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 is, what is the ground state electron configuration of oxygen? Okay, so oxygen. And when we say ground state configuration, this just means that electrons in the oxygen atom weren't lost or gained. So when we want to find the electron configuration, we do a set of steps. So the first is to divide your periodic table into the different orbitals. So for example, the S block is this, the left 2 columns here. The P block is this whole green rectangle. And the D block are the middle transition metals. And the F block are the last 2 rows, which are the lactanides and actinides. So starting from hydrogen, we move left to right across the periodic table, writing the row number and then the block letter right after it until we get to our desired element. So in our case, this is oxygen. So oxygen is found right here, atomic number 8. So that means it contains 8 protons and 8 electrons in its ground state. So after we write down the electron configuration, we can double check that it's right if we count out the number of electrons that can be summed up in the superscripts of our electron configuration. So starting from hydrogen, I'm going to write the row number, which is 1, and then the block letter, which is S, and then a superscript of 2 to show that there are 2 electrons in this orbital. And this corresponds to the same as hydrogen and helium's electron configurations. So then moving down to the next row, we have 2s2, and then across to 2p, and then we count up to oxygen, so 1, 2, 3, 4. So the electron configuration of oxygen is 1s2, 2s2, 2p4. And we can double check by adding up all the superscripts to make sure that we have 8 electrons. So 4 plus 2 plus 2 is 8. So we know that this is the correct answer. Now let's see what the junior tutor said. 1s2, 2s2, 2p4. Explanation: an electron's electron configuration, or an element's electron configuration, is a numeric representation of its electron orbitals. Electron orbitals are regions around an atom's nucleus where electrons are likely to be located. An electron configuration can tell a reader how many electron orbitals an atom has, as well as the number of electrons in each of its orbitals. So it shows the distribution of electrons of an atom in a molecule. The area where the electrons orbit is called an electron shell. As an atom or molecule gains electrons, they fill different orbital sets according to a specific order. So each set of orbitals contains an even number of electrons when full. The sets of orbital are the s, which can hold 2 electrons, the p, which can hold 6, the d can hold 10, and the f can hold 14. So when writing electron configuration, you first find the electron's atomic number. Each atom has a specific number of electrons associated with it. Locate the element's chemical symbol on the periodic table. Number 2 is to determine the atom's charge. Uncharged atoms will have exactly the number of electrons as represented by the atomic number. 3 is to write the electron configuration notation. Electron configurations are written so as to clearly display the number of electrons in an atom as well as the number of electrons in each orbital. Each orbital should be written in sequence with the number of electrons in each orbital written in the superscript to the orbital name. The final electron configuration is a string of orbital names and superscripts. Step 4 is to fill in the orbitals according to the number of electrons in the atom. And then in writing the electron configuration, we fill in the electron orbitals starting with the lowest energy, following the Aufbau, Pauli exclusion, and Hund's rule. Ground state oxygen atom has 8 electrons. The first 2 will go into 1s, next 2 go into 2s, and the last 4 go into 2p. Yep, so this solution is correct.
To write the electron configuration for argon, we first need to figure out how many electrons there are in the argon atom. We can do that by looking at the periodic table and finding the atomic number for argon. That's the number above the element symbol. It tells us the number of protons, but it also tells us the number of electrons. And once we have the number of electrons, we can begin to write the electron configuration for argon. We use the chart on the right to help us write the notation for argon. We'll go down the first row, and that we have the 1s. S orbitals can hold up to 2 electrons, so we'll put a 2 after the s. We'll go down the next row, we have the 2s, s's can hold 2, and then to the third row where we start with the 2p. P orbitals can hold up to 6 electrons, so let's put 6 electrons in this 2p orbital. That gives us a total of 10. Since argon has 18 electrons, we need to have 8 more to finish the configuration. Still in that third row, we go to the 3s. Let's put 2 there, and then we go to the fourth row, which starts with a 3p. P's can hold up to 6. We already have 12, so if we put a 6 in that p, we have 2 plus 2 plus 6 plus 2 plus 6. That gives us 18, which is the number of electrons for the argon atom. This is Dr. B with the electron configuration for argon. Thanks for watching.